Fan for many, many years. I read your book, The Physics of Star Trek. I recommend that to anybody. You've written A Universe from Nothing. It came out earlier this year. Tell me about yourself, what you're doing, just a quick overview.
I'm a theoretical physicist who does everything from particle physics to cosmology. I study the early universe and the late universe, and every now and then everything in between, trying to understand how we got here. I direct something at ASU, a wonderful institute at Arizona State University called the Origins Project, which looks at everything from the origins of the universe to the origins of consciousness, and run meetings, scientific meetings and public events on those fascinating topics. And of course I write some books and also write commentaries for newspapers and magazines and do some TV. That's about it, basically. Now my research areas are mostly the areas of dark matter and dark energy and the possible phenomena that happened in the very early universe where we need to understand particle physics to describe them.
You're a theoretical physicist, right?
Yes, I'm a theoretical physicist. That means I don't do experiments. I work with computers and pens and paper.
Now, I think people assume that all theoretical physicists these days are into the string theory. Are you?
Not particularly. I mean, there are some interesting ideas associated with string theory. It's not true that all theoretical physicists are doing string theory. There was a little while when many of them were, but string theory's fallen on hard times, and it's a fascinating theoretical idea that hasn't yet had a great deal of success in trying to describe our universe. We don't even know if it does describe our universe, and therefore, while it's interesting, it's not, as I like to put it, not yet ready for prime time.
Is it just me, or is physics not stagnating a bit? We haven't had an E equals MC squared for a long time.
No, well, I don't think it's stagnating. We just had an incredible discovery that we think we've discovered the Higgs Boson, and that caps one of the most remarkable theoretical and intellectual journeys that humans have ever taken. So that's certainly remarkable. And then the discovery of dark energy. So the theoretical discoveries have been profound over the last few years and changed our picture of the universe. It's true we don't have a new Einstein, or at least we don't have a new theory of quantum gravity yet. But so theory was very successful in the 1960s and 70s. We started 40 years ago understanding one of the four forces in nature, and now we understand three of them completely as quantum theories with a kind of unified framework. It's been a really amazing saga, and it's unheralded. And of course, what that means is experiment is now, you don't have those kind of remarkable theoretical advances every year. And now experiment is leading the way, I would say, and demonstrating in certain cases things that we had never predicted, and in other cases validating the predictions we made 40 years ago. And so it's time to now look forward and see where we can go from here.
So this whole CERN thing, as far as you're concerned, is a success?
CERN is a success? Yeah, it's an amazing success. It not only is a success because it made a great discovery, but it's demonstrated science at its best. The CERN is, major accelerators today are like the Gothic cathedrals of the 21st century. And they're the most amazing machines humans have ever built. The fact that they work is remarkable. They're built by thousands of physicists from hundreds of countries speaking dozens of languages. And they demonstrate that science is a truly international activity. And every collision generates hundreds of terabytes of data, and there are millions of collisions every second. Every second, more information is generated at CERN than is contained in all the libraries in the world. And just learning how to handle that much information and work with it is amazing. So it's really a testimony to the profound intellectual curiosity that humans have, and what we can do if we put our minds to it.
Seinfeld said, even nothing is something. You're saying the entire universe comes from nothing.
Yeah, and I think Seinfeld was right. Of course, not for the reasons he would have suggested, but nothing and something are not so different anymore. That's part of what I talk about. I mean, the classical ideas of religion and philosophy about nothing and something have to be refined as we talk about what we mean by nothing. And nothing is a physical quantity. And what do you mean by nothing? And I try in my book to talk a lot about it. And what we've discovered is that the entire universe, all 100 billion galaxies and 100 billion stars in each galaxy, has the properties we would expect of a universe that arose from nothing. And by nothing, I mean no particles, no radiation, no matter, and maybe no space and no time. And if you ask what would the universe look like that had those properties, then you would it turns out to be that our universe has the properties of just such a universe. And does that prove we came from nothing? Absolutely not, but it makes it plausible.
I mean, I picture the Big Bang as some awesome explosion.
Well, it's an explosion, but not in the classical type. It is an awesome explosion, but it's not in a single point. Normally when a bomb explodes, it happens at a single point in space. The Big Bang happened at every point in space at the same time. And so it's not as if we're all emanating. The entire universe was in a very small region, and maybe even at a single point. But when we think of it now, it happened everywhere in the space that we now... Space itself started expanding, and the Big Bang happened everywhere. And that's different than a... So this idea of an explosion in a space that already existed is not the Big Bang.
I think that's a mental picture many people would have, though, it expanding out into the universe forever, or perhaps contracting.
It is a mental picture, and that's why I wanted to disabuse people of that notion, because it's a mental picture that's incorrect. The universe is a vast, expanding region containing, as I say, maybe over 400 billion galaxies, of one of which is the Milky Way, and it's expanding uniformly in all directions. And one of the biggest surprises is that expansion is speeding up instead of slowing down. Any sensible universe should slow down, but our universe is speeding up, and that was one of the biggest surprises of the last century, and was discovery that was made less than 15 years ago. They weren't looking for it; they were trying to measure how the universe slowed down.
Was it assumed until that point that it was actually slowing down?
Because gravity, as you may have learned in high school, gravity sucks. It always pulls, it never pushes. And a universe dominated by gravity, you'd think the gravitational attraction of all the stuff in the universe would cause that expansion to slow down. Stuff would move apart ever more slowly. If I throw a coin up in the air, usually it slows down and sometimes comes back. But never does it speed up, because you need some kind of cosmic anti-gravity for that to happen. And that's what apparently is dominating the universe at the present time.
Could you explain the Doppler effect and how that works in relation to expansion?
The Doppler effect is really quite simple. I think in the lecture I point out a cartoon that I liked of two cowboys on the plain looking at a train, and one says, "I love listening to the lonesome wail of the train whistle as the magnitude of the frequency changes due to the Doppler effect." It's the simple fact that a train whistle sounds higher when it's moving towards you, or lower when it's moving away from you, because the sound waves get scrunched up in front of the train, and their wavelength gets smaller, and their frequency gets higher, and therefore the note sounds higher, and the sound waves get stretched behind the train. Same with an ambulance and all of that. It's a familiar phenomenon of many people. Well, it turns out for different reasons it's true in our universe, that as we look out at distant galaxies, the light from those galaxies is systematically stretched. And for different reasons, because it involves relativity, it tells us those galaxies are moving away from us. And by the amount by which the light is stretched, and longer wavelength light is the red end of the spectrum, so we say those things are redshifted, and we're finding that the more distant objects have greater and greater redshifts, meaning that objects that are farther away from us are moving away from us faster, and moreover, that almost all galaxies are moving away from us. The universe is indeed expanding. That does not imply we're in the center of the universe. It implies that we're in a universe that's expanding uniformly in all directions.
So this is considered scientific fact?
Yeah, absolutely.
Could we cease to exist?
We can always cease to exist at any moment, but the expansion is happening in a well-defined way, and it's not going to affect us in a dramatic way. Eventually, the rest of the universe will disappear before our very eyes, but not our very eyes, because the disappearance will take about 2 trillion years to happen. So we won't be around for it. But maybe observers on a planet around another star in our galaxy 2 trillion years from now will look out and they won't see any of the other 100 billion galaxies that we now see, because they'll all have disappeared. Because they'll be moving away from us faster than light.
Some of this is hard to grasp.
Of course it is. It's very hard to grasp, and it's amazing that we've been able to grasp it. It's just truly amazing that we, in this puny place in the middle of nowhere on a planet that's not particularly special, around a star that's not particularly special, have been able to, with our telescopes and our ideas and our mathematics, been able to ascertain these amazing things about the universe. They blow your mind. They're truly the most amazing discoveries humans have ever made, and that's why we should share them more broadly.
Is this not just scientific arrogance, though? Disregarding of religions, of Genesis?
I don't know whether it's arrogance. It's the way the world works. It's the opposite of arrogance. It's we let the universe. Religion is arrogance, because religion says you know the answers to the questions before you even ask them. Science says we in order to determine the answers, we go out and ask the universe questions. We don't presume to know the answers. We let our beliefs conform to the evidence of reality rather than the other way around.
So when you ask yourselves the question, how old is the universe? How do you solve that?
Well, we try different ways to measure the age of the universe and see if they all agree, and they do. One of the ways we can do it, of course, is by looking at the age of elements and determining, the abundance of various radioactive elements, and we know at which rates they decay, and that gives us one estimate. Another is, very simply, if you were driving between Vancouver and Seattle, and you were going 60 miles an hour, or 100 kilometers per hour in Canada, if I noticed that, if I called you up and said, how far away from you are you now, and you said 200 kilometers, I'd say, oh, you've been driving for 2 hours. Well, we look out at the galaxies, we measure their distance and their speeds, and we work out how long it would have taken before, if they all started out in the same point, to get to where they are, and we get another estimate for the age of the universe. Another estimate of the age of the universe is we calculate how fast the universe should be cooling down if it's expanding, and we measure the temperature of the universe. And what is amazing is all of these things converge on precisely the same number, and that is what has been amazing. And again, only in the last decade have we gotten that number, and that number is 13.72 billion years. I would never have thought in my lifetime, in fact, that we would have been able to know the age of the universe with that kind of accuracy.
Dark matter, that's all the rage these days. Everyone talks about dark matter. Is that the nothing that you're discussing here?
No, that's not the nothing. Dark matter is actually quite something. It's material. It's just not made of the same stuff as you and I. The nothing I'm talking about is literally empty space. If you take a region of space and get rid of all the particles and all the matter and all the radiation and everything, what we discovered is that empty space weighs something, and that is truly remarkable.
But that's not nothing then. That's something.
Why?
Because only matter has mass.
No, well, this doesn't have mass. It has energy, but there's nothing there.
But energy equals mass times the speed of light squared. So.
No, not necessarily. And you could turn that, if certain types of energy can be converted to mass, but this is the energy of nothing, and it's not contained in any massive objects. It is literally empty space. So I'm trying to tell you that emptiness is much more complicated than you would have thought beforehand, because it depends on quantum physics. But in fact, what I'm telling you is that if you take a region of space that has no particles in it, no radiation, nothing, you can look at it and with a microscope and there'll be nothing there. It still has energy, and that's one of the biggest mysteries. We don't know why. It's one of the biggest mysteries in science right now. But it's changed completely what we think about as the definition of empty space. And it's changed our understanding of the future of the universe. It turns out that we know that empty space is full of these virtual particles. They're not real. You can't measure them. You can't see them there, but in fact they have an impact on everything else in a way that we can calculate. So we know they're there even though we can't see them. But there are no real particles there, and they impact the properties of matter in a way that we can calculate, and we get the right answers to 9 decimal places. So it's one of the great triumphs of theoretical physics. But then when we try and calculate what they might do to empty space, we come up with an answer which is completely wrong. And it's a big mystery. There's something we fundamentally don't understand when it comes to quantum mechanics and gravity, and maybe someday we will. But what it's resulted in is that one of the things we do know is if you put energy in empty space, it's gravitationally repulsive, not gravitationally attractive. And therefore, it will cause the expansion of the universe to speed up. And that's what's been measured. That was the big surprise in 1998, which led to the Nobel Prize this past year for the people who discovered it.
Is the universe flat or curved?
Well, we've discovered empirically that the universe is flat. And by flat, I don't mean flat like a pancake. I mean flat like in the sense that the universe is, it can be curved in 3 dimensions. And of course, we can't picture curved 3-dimensional universes because we're 3-dimensional beings. So obviously we can't picture. We can mathematically write down what those things mean. But a flat universe is just the one you always thought you lived with, namely where the x, y, and z axes are point in 3 perpendicular directions and they remain the same throughout all of space. In a curved universe, those 3 axes can move and curve, and parallel lines can curve as you move throughout space. But a good old-fashioned flat universe is the one where light travels in straight lines and straight lines remain straight. It's the sensible universe you always thought you lived in.
So Einstein was wrong. Didn't Einstein not say that space was curved?
No, he said that matter curves space. So locally, there can be little bumps. But his theory wasn't wrong at all. It told us that the universe can exist in one of 3 states, either flat, open, or closed, they're called. One of 3 different kinds of geometries. And the big holy grail of physics for the 20th century was trying to determine which geometry we live in. And one of the great triumphs of observational cosmology is that by the end of that century, by the year 2000, we had determined pretty convincingly that we live in a flat universe. But there's not enough matter to make the universe flat. We were missing 70% of the energy of the universe that didn't seem to reside in galaxies or even dark matter. It wasn't anywhere we could see around galaxies. So the only place it could be is where galaxies weren't. And what is where galaxies aren't? Well, there's nothing. And amazingly, if you put energy in nothing, you'll cause the universe to speed up. And what did they discover independently? The universe is speeding up. So all of the data fits together with this cockamamie universe dominated by the energy of nothing. And and almost all the rest of it is dark matter made up of some new type of elementary particle that's not the stuff that makes you and I up. So you and I are a 1% bit of cosmic pollution. We could take everything we see in the night sky, all the stars and galaxies and planets and everything beautiful in the universe, and get rid of it, and the universe would be largely the same.
If I were to take all the mass in the universe and take away all the nothing, how much physical space would that occupy? Size of the Milky Way?
I'm sorry, if we were to do what?
If I took away all the nothing, all the dark matter, and compressed all the actual mass of the universe.
Well, you can compress it into as small regions you want. All of the 100 billion galaxies we now see, all the mass in those galaxies was in the early history of the universe contained in a region smaller than an atom. It's hard to imagine, but it was true.
I asked a guest 2 weeks ago, what is time? I'll ask you the same question. What is time?
Time is the thing I wish I had more of.
We only have about 5-10 minutes here.
It seems to be, it's very interesting because relativity unifies space and time in a kind of 4-dimensional universe, but time seems to be very different in space. I can do round trips in space. I can go to Vancouver and back, but I can't seem to go back to my childhood and back. Mm-hmm. And so time is somehow different, and general relativity tells how time and space are related to the presence of matter. But at this point, time is a variable like space. Space tells you where you are in the universe, and time tells you when you are in the universe. But it's a local quantity, and it seems that for individual observers, they can only move in one direction, and we're not quite certain why.
Would it be possible to observe the creation of a new universe?
No, probably not, because even though it might be possible, for that to happen, it would very quickly pinch off and basically from the outside look like a black hole. So we wouldn't be able to see what was going on in that universe.
Are they not trying to recreate the Big Bang over there at CERN?
Well, we're recreating the conditions very shortly after the Big Bang. But not the Big Bang itself. No, we're trying to locally create temperatures and energies that describe how the universe existed very shortly after the Big Bang. And over a microscopically small region instead of over something that is like the size of our universe.
Is it all media hype, this speculation that CERN is going to kill us all?
Of this media hype, yes.
In science, nothing can ever be 100% true.
Well, in science we don't deal with truth, we deal with falsehoods. Namely, we test ideas, and if they don't agree with the experiment, we throw them out, and what remains isn't necessarily 100% true, but it gives us a closer approximation of the truth.
But in theoretical physics, do you not create an idea and do experiments to see if it's true?
Well, and sometimes it works a variety of ways. Sometimes the experiments lead, like they did with dark energy. We don't understand it. So sometimes the experiments tell us something that we can't understand, and we try and understand it. Sometimes as theorists, we propose new experiments that haven't been proposed as a way of testing our ideas. So it works both ways.
Lawrence, you've written this book, A Universe from Nothing. You've written several books. They're all great. Why this one?
Well, there are a few reasons. One, I had given a public lecture, and it turned out it became kind of a YouTube sensation. Over 1 million people, 1.5 million people have now watched it. And I thought, well, there's clearly a great deal of interest in this. And moreover, a lot of questions have arisen based on the lecture. And I thought I could present a small, short, cogent history of our current understanding of the universe, of describing some of the most remarkable results that people have come up with and that aren't really well known. And I thought I could do it in a way that might be accessible, and so I decided to do that. And at the same time, I thought I could address, often in the process of lecturing the subject, I get hit with religious questions like, how can something come from nothing? And I thought I could address the fact that that it is remarkable that we don't seem to need any supernatural shenanigans to make it all work.
On that topic, what is the genesis of the human being?
Of a human being? Well, that's well documented. Evolutionary biology has followed the evolution of life from at least the first single-celled animals to today, and it's been a remarkable history over the last 4 billion years. We don't yet know the origin of those first single-celled animals. We don't know how chemistry turned into biology, but I fully expect in maybe in the next decade to have that answer.
What I found incredible, and I did watch that lecture, was that it's only due to the supernova.
Oh, that origin, absolutely. I wrote a whole book about it. We are all stardust. Every atom in our body was once inside of stars that exploded, because the only elements that were created in the Big Bang were hydrogen and helium and a little bit of lithium. But lithium is important to some people, but the important stuff, nitrogen, oxygen, all the rest, that's only created in the cores of stars, and the only way that can get into our bodies, if those stars were kind enough to explode, because they spew out all the material they created, and over the years, over many 7 billion years or so, that material built up until 5 billion years ago, another star exploded, compressed the region of gas in our neighborhood, and caused our sun to start forming and the solar system around it. So every atom in your body was once it started exploding, maybe even different stars. In the left hand, one star, in the right hand, another, or maybe many stars. So you really are stardust. You really are a product of the most violent explosion that's ever happened in all of nature.
So if we could create a new universe, it would not even get pollinated to sustain life for approximately 7 billion years. There's a dormancy period, it seems.
If we're any example, I don't know if life evolved elsewhere in less time, but certainly you need time to make up the heavy elements, at least to make up the life we know. You can't do it without carbon and nitrogen and oxygen, and that takes a while.
Has that process stopped, or are new elements being created as the universe is expanding?
The process is continuing. Stars are being born all the time and dying all the time. So the abundance of elements in the universe is changing all the time.
So elements are changing and new conditions can arise.
Well, yeah, absolutely. And I talk about that. In 1 trillion years, most of the universe will be helium. Right now, 24% of it is. But in 1 trillion years, over 60% of the universe will be helium. So the conditions of the universe change. But again, part of the cosmic conceit that people seem to have is this notion that the universe is the way it is now is the way it's always going to be, and that's just not the case.
Is there any lectures that you have coming up, Lawrence?
I always have lectures coming up. I have some in England. You can go to keep track of what lectures I have and where. You can go to my webpage, which is www.krauss.faculty.asu.edu, and there's usually up-to-date information on what lectures are coming up.
And again, I have to recommend everyone buy The Physics of Star Trek if you're a fan of the show. It's a must-have.
I like to think so, and it's been updated a few times to take into account the new show. So
I've lent that book out to 5 different people, Lawrence. 3 of them have actually returned the book, so I've purchased it a couple of times myself.
Oh, well, that's good. But what you should do is convince them to buy the book instead of lending it to them.
I will from now on. Don't worry. Where do I purchase the book?
You can purchase them, hopefully at a bookstore near you. The new book, Universe of Nothing, has been a New York Times bestseller, so it should be available in most bookstores. You can get it on Amazon or Barnes & Noble.
Yeah, this thing went bestseller in, what, a week?
Yes, a week after it came out. It was kind of a surprise, yeah.
Lawrence, an honor to have you on the program. I know you're a busy guy and you've got to run to another seminar or lecture or something, so we'll let you go, and thank you so much for being on the show today.